in gamma decay. Next topic is angular momentum and parity selection rules. A classical electromagnetic field produced by oscillating charges and currents transmits not only energy but angular momentum as well. And this is an older concept according to our classical electromagnetic. If, for example, we surround the charges and currents with a large spherical absorbing shell, the shell can be made to rotate by absorbing radiation. That means angular momentum means it is a rotating property. So when from a source, if you are getting charges, etc., by absorbing that, this may rotate. That means it is getting angular momentum. The rate, that means that source is transferring angular momentum to this. That is a point. So the rate at which angular momentum is radiated is proportional to the rate at which energy is radiated. That is always a connection between, as you know, between angular momentum and energy. When we go over to quantum limit, we can preserve the proportionality if each photon carries a definite angular momentum. The multipole operator of order capital L is associated with an angular momentum L. We have already denoted the multipole order as L, and actually that letter L was used because it is related to the angular momentum, or it depends on angular momentum. We therefore conclude that a multipole of order L transfers an angular momentum of LH cross per photon. And now consider a gamma transition from an initial excited state of angular momentum I. This I, as you know, it is the total angular momentum of nucleus, or sometimes you are considering it as the spin of nucleus. I and parity pi I to a final state IF and with the parity pi F. Initially you are assuming that I not equal to IF. So by the principle of conservation of angular momentum, I you can write as L plus IF. This is somewhat similar to that we have done in beta decay. Since L and IF must be a closed vector triangle, that means they are vector quantities, the relation should be satisfied in vectorization. The possible values of L are restricted. The largest possible value of L is, so that is our vector concept. That means this L you can write as simply I minus IF. So the value of L can be I plus IF, and the smallest possible value is magnitude of II minus IF. So this is the same case that we are getting in your J, LS coupling, etc. teams. They are getting the same result here. For example, if II equal to 3 by 2 and IF equal to 5 by 2, the possible values of L are, you can add them, it will be 3 by 2 plus 5 by 2, 8 will be, 5 plus 3 is 8, 8 by 2 is 4, and subtracting this 5 by 2 minus 3 by 2 is 5 minus 3 is 2, 2 by 2 is 1. So maximum value is 4, minimum value is 1. So the possible values of L are from II plus IF to magnitude of II minus IF. That means from 4 to 1. That means 1, 2, 3 and 4. The radiation field in this case would consist of a mixture of L is equal to 1 for dipole, L is equal to 2 for quadrupole, L is equal to 3 for octopole. That means you are writing it as 2 raised to L format. So 2 raised to 3 is 8. That is known as the octopole. This is quadrupole, this is octapole, and this is hexadecapole. Hexadeca means that is 16 2 raised to 4 radiation. Whether the emitted radiation is of the electric or magnetic type is determined by the relative parity of the initial and final levels. If there is no change in parity, that means you are writing as delta pi is equal to no, which means that normally you are writing as if pi I equal to pi f and pi I can be minus pi f. There is you are writing parity as minus 1 raised to L. That is already we have discussed. So if initial and final parities have same value, that means one is positive, the other thing also should be positive. Then only, or if minus 1 raised to L is even, that means minus 1 raised to L is 1, you will say that that means L is its final value. There is no change in parity, both positive. And if one is positive, other is negative, you can say that parity is changed. But if there is no change in parity, delta pi, that means no, then the radiation field must have even parity. If the parity changes in transition, that means delta pi is equal to yes, then the radiation field must have odd parity. And the parity selection rule for fields, this pi of this ML stands for magnetic multipole, EL for electric type multipole. It is to minus 1 whole raised to L plus 1, and for electric you are writing as minus 1 raised to L. So you can see the difference, that minus 1 raised to L was the term that we have used in beta decay, and that equation is here applicable only for electric, and for magnetic you are taking it as L plus 1. So you can see that for a particular value, say if 2, this minus 1 raised to 2 is 1, that means L is even. But the same value for magnetic you are getting as minus 1 raised to 2 plus 1, that is minus 1 raised to 3, that is minus 1. So for a particular L value, if E, that for electric field is even, for the same value of L, the parity of magnetic field is odd. And for a particular value, if parity of E is odd, that means if it is 3, minus 1 raised to 3 is minus 1. The same thing, L value, 3 plus 1 is 4, minus 1 raised to 4 is plus 1. That means for the same value of L, for electric multipole radiation, if it is odd value, corresponding magnetic field is even. That we are saying here. Electric and magnetic multipoles differ in their parities. Electric transitions have even parity if L equal to even, while magnetic transitions have even parity if L equal to odd. Therefore, a pi equal to no, that means no change in parity, transition would consist of even electric multipoles and odd magnetic multipoles. Delta pi is equal to yes transition, on the other hand, would consist of odd electric and even magnetic multipoles. And we can have our previous example. II equal to 3 by 2 to IF is equal to 5 by 2. Let us assume that pi I equal to pi f. That means no minus sign here. So that delta pi equal to no. So we have L is equal to 1, 2, 3, 4. Then when L is equal to 1, radiation must be of magnetic character. That means L is equal to 1. This equation, our L is 1 and there is no change in parity. So when there is no change in parity, it is a delta pi equal to no, that means parity should be a positive quantity or it is even. So if here you can say that for L is equal to 1, for electric you can consider, you will get it as a -1 value, and for magnetic 1 plus 1 is 2, you are getting it as a plus value. So if parity is not changing in that particular one, so definitely it must have a magnetic one, and electric transition have a change, so it is not possible. That is why L is equal to 1, radiation must be of magnetic character, that means odd magnetic and even electric multipoles for delta pi is equal to no. This we have mentioned earlier. The L is equal to 2, radiation is of electric character. Why? Odd magnetic and even electric multipoles for pi is equal to, and so on. That means for L is equal to 3, you have magnetic character, L is equal to 4, electric, etc. So the radiation field must be of the form M1. So M for magnetic, and this first one, letter 1 for order. That means L is equal to 1. This is dipole, and this is quadrupole. E2, M3, and E for radiation. If our state has delta pi is equal to pi I equal to minus pi f, that means delta pi is yes. That means you have odd electric and even magnetic multipoles for delta pi is equal to yes. That you can verify. That means for odd electric, that means this one. If parity is changing, that means when L is odd, then you are getting this value as -1, and you are getting this value as -1 when this L is even. So means this is -1 when L is odd, and this is +1 here. This is -1 when L is even. That is why for the two systems we have mentioned pi is equal to minus pi f, odd electric and even magnetic multipoles for delta pi is equal to s. Then the radiation field would have E1, M2, E3 and M4 radiation. Similar things. So now we can specify the angular momentum and parity selection rules as the L value should be between II minus IF to II plus IF. It means L greater than or equal to II minus IF and less than or equal to II plus IF, and no L equal to 0. This is an important conclusion. And delta pi is equal to no even electric and odd magnetic. Delta pi is equal to yes, odd electric and even magnetic. So the last two are the parity selection rules, and this is the angular momentum selection rule. And why this L is equal to 0 is not possible? The exception to the angular momentum selection rule occurs when pi I equal to pi f, because there are no monopole, that means L is equal to 0 transitions in which a single photon is emitted. We have already the concept that we have only electric monopole, that means single charges, and no magnetic monopoles. Classically, the monopole moment is just the electric charge, which does not vary with time. A spherical charge distribution of radius R gives only a pure 1 by r square Coulomb field for r greater than r. Even if we allow the sphere to undergo radial oscillations, the Coulomb field for r greater than r is unaffected, and no radiation is produced. That means if charge is oscillating, it is not varying its quantity. That Q is remaining constant, and for calculations you are considering that Q as a point charge, and we are not bothering about the dimension of charge. For transitions in which II equal to IF, the lowest possible gamma ray multipole order is dipole. That means L equal to 1. That means this IA equal to IF condition. The case in which either II or IF is 0, it is particularly simple. And we have mentioned that if IA and IF, they are non-zero values like your 3 by 2 and 5 by 2, we have shown that the gamma ray transition is a mixture of multipoles. That means dipole, quadrupole, octapole, etc. You can have the combination like E1, M2, E3, M4, or like M1, E2, M3, E4, etc. Combination like that. So at the same time, you can have E1, M2, E3, etc. But if it is a pure multipole transition, that means only you have say E1 or M1. Such case is possible only when IA or IF is 0. Here only a pure multipole transition is emitted. For example, the first excited, that means II equal to 2. That means the excited state is at IA value 2, and this, as you know, this plus means parity is positive. That means delta pi is equal to pi A is even. That means your parity is not changing in that quantity. That means pi A, how can you take parity as even? Minus 1 raised to L value you are normally considering for nuclei. So when that L is even value, parity is considered as, that means when minus 1 raised to L is 1, parity is even. When minus 1 raised to L is odd, parity is considered as odd, and you are writing it as minus 1. So 2 plus, that means parity state is plus. IA is equal to 2 state in even Z, even N nucleus decays to a 0 plus ground state. And this is known to us. For even Z, even N nuclei, the nuclear angular momentum or nuclear spin you are normally taking as 0. Means the spin you are getting as when you have the spin is due to unpaired nucleons. That concept already we already know that. For example, if you have oxygen 16, you have 8 protons, 8 neutrons. So the resultant spin is 0. But if 1 is extra, that means you have only 8 protons and say 7 neutrons, there is a possibility for a single nucleus. So here that means even Z, even N nucleus, normally their ground state have 0 spin. But this is already known to us. You have studied that type classification in your spectroscopy. For the excited state, there may be a variation in spin. So for ground state, you have 0. But for the upper state, you are getting it as 2. So when the transition is from II, that means upper state you are taking as II and the lower state as IF, the transition is from 2 plus states to 0 plus state. So the above selection rule gives immediately. So from a value to 0, you can have 2 plus 0 to 2 minus 0. Always it is 2. So purely it is L is equal to 2 and electric radiation for pi equal to no. That means we know the selection rule as minus 1 raised to L for electric and minus 1 raised to L plus 1 for magnetic. So here L is equal to 2. So minus 1 raised to 2 is plus 1. That means parity, no change. And for magnetic, minus 1 raised to 2 plus 1, it is minus 1. So there is a change in parity. So for this transition, we have a 2 plus stage as well as 0 plus stage. So plus 2 plus means no change in parity. So delta pi is no. So delta pi is no means that transition should be purely electric. So you are getting an electric radiation or electric dipole radiation. That means L equal to 2. That is, the transition is through the emission of a pure electric quadrupole. I am sorry, I have mentioned that E is equal to as dipole. It is a quadrupole 1, quadrupole E2 transition. For II equal to IF equal to 0, the selection rules would give only L equal to 0. This we have mentioned here in selection rule. No L equal to 0 is possible. That means IA equal to IF, which, as we have already discussed, is not permitted for radiative transitions. A few even nuclei. Why we are calling the even is clear with our earlier discussion. The even nuclei have 0 plus first excited states. Normally, that is true. The ground stage for even is clearly with the 0 spin. The upper or higher states may have a change in spin. But for some nuclei, the excited state also have 0 spin. So you have a 0 plus spin to 0 plus spin stage. That means L is equal to 0. Because IA minus IF must be equal to 0 here. So that transition is forbidden. So 0 plus first excited stage, which are forbidden to decay to the 0 plus ground state by gamma emission. So how it is possible for such transition? There, that difference in energy is not emitted as gamma, but that difference in energy is given to one of the orbital electrons. And that property we are already studied in your radiation physics, and it is known as these states decay through internal conversion. That energy is transferred to one of the orbital electrons and they are emitted. So that is the possibility for, or why this internal conversion is getting. And we have studied that this gamma emission and the internal conversion, they are competing in nuclear decays, that we have already mentioned. So there is a competition there. But when it is from 0 to 0 transition or 0 plus to 0 plus transition, it is definitely internal conversion is taking place and no gamma emission is possible. So we have our selection rules for angular momentum and parity, and that special condition L is equal to 0, why it is not possible, we have now mentioned. And that's all in this lecture. Thank you.